Okay. Okay. Hello, everyone. I think it's time we start. So welcome. Solving tricky coordination problems in stateless .NET services. So the topic of this talk is basically trying to show you something that I realized in my previous jobs, where normally when you scale out an application and you have multiple instances running at the same time, you usually expect that the more independent they are, the easier it is to operate them. But there is a thing that I noticed where at an abstract level sounds counterintuitive, where occasionally your applications want to do something that does require some level of coordination between the instances. And if you don't allow that to happen, then you end up with more operational problems than you would expect. So this is what I'm going to try to show you with this presentation. And then at the end, I'll demo a library that I wrote, a sample library that kind of tries to make to show you a concrete solution to some of these problems. So with this in mind, let's get started. My name is Loris Crow. I'm a developer advocate at Redis Labs. I'm Loris on Twitter. I'm from Italy. And that's just a photo of me doing scuba diving. So normally, when people want to talk about communication patterns in distributed systems, they mostly talk about inter-service coordination. So service A communicating to service B. Which is fine. There are a lot of interesting things to say on the subject, like event sourcing and the language that different services have to share and all this kind of stuff. But in this session, as I mentioned earlier, I want to focus on what happens within a single service. And in fact, whether you have 100 services in your microservice architecture or you just have one big monolith, for the scope of this presentation, it doesn't really matter, because I want to see what happens inside the service. So let's zoom in and forget all about other services. So when we pick inside the box of a service, we rediscover that services are actually made up of different pieces that work together. And in this image, we have two instances of the same application with a load balancer sitting in front of them. And here you can see that these two boxes represent two copies of the same application. And these could be two processes, two containers, deployed on the same machine, on different machines. Again, for the scope of the presentation, the deployment details don't matter. What matters is that you are scaling horizontally or scaling out. Like they say on Azure. Let me start with one common coordination problem, and in the meantime also introduce a very useful practice, which is making applications stateless. So let's say that your application is an e-commerce website. We have an item catalog that sits in our main database, and each user has a shopping cart, and they can fill it by browsing the website. So where should user shopping carts live? A reasonable answer would be inside the session, but there are some things to consider. So starting with the basics, enabling sessions in ASP.NET Core is very easy. It's just a couple of configuration lines, as you can see. It's just add session and use session. And with this configuration, the session state is stored in our application's memory and is connected to a specific client by a cookie that contains the session ID. After we are done enabling it, then we can access the session object from the HTTP context of a request, and the object will be the same across different requests coming from the same browser. And if you Google shopping cart ASP.NET, you can find plenty of tutorials that teach you to build carts this way. But there are two problems with this setup. First of all, if we keep this data in memory, we bring upon ourselves a huge amount of operational problems. Because if we have more than one instance of our application, again, so if we scaled out, or scale horizontally, then we will need to route all requests from the same session to the same instance, because otherwise the customer will lose their cart. Because if the request goes to another instance that doesn't have the right session state in memory, the user will be very confused actually, because they will have like a flickering experience with their shopping cart. It kind of works, kind of doesn't work. So And to make sure you route all requests always to the same instance, you need to use a configuration option in the load balancer called sticky sessions, which have also the side effect of making dynamic scaling really annoying. And it's not just that, also deploying updates is going to be painful because every time you restart the application, sessions are going to disappear. People are going to lose their card. And the fix to this is fairly simple and I think fairly commonly known. Usually what you want to do is you want to move the session data in a memory database, like Redis. This is where Redis comes in, right? So once you do that, you don't need sticky sessions anymore. You could also store sessions in the main database, but that's usually a problematic idea because you need the session data for every request that the client makes, and that becomes unsustainable after a while because once you get past a certain load, like users tend to get to a point where they overpower your database. So to keep things fast, this is where people usually rely on Redis or similar solutions. So how do we stop storing sessions in memory and move them to Redis? Again, in ASP.NET Core, it's a couple of configuration lines, nothing more complicated than that. Add distributed memory cache and add stack exchange Redis cache. Stack exchange is part of the method name because ASP.NET Core is using the Redis client developed by Stack Exchange. Once you do this, no more sticky sessions, which is great. But if you remember, I mentioned two problems. So the first one we just solved by moving sessions to Redis. But there's a second one still standing. And that is that in ASP.NET Core, sessions are browser sessions, not user sessions. So this means that if we were to save the card state directly in the session object, the same user would see two different cards when logged in from two different devices. And maybe that's what you want, but probably it's not. Because normally you want your users to be able to switch device and continue building the same order, but again, it might depend on your use case. So how do we fix this? Again, the fix is not particularly involved. All we need to do is to keep inside the browser session a reference to the user ID, and then use that information to store and load the card data using the IDistributedCache interface. So if you look at this code, here, I'm injecting a cache instance into my controller, and then when I want to get the card, I'm using get a sync from that same object. Notice one thing, though, that this is a big difference between the session object and the IDistributedCache interface. The cache is not session specific, so you can think of it as a dictionary shared by all the requests. So we need to specify in the key name whose card we want to fetch. And this is why we are storing in the browser session the user ID. So now, if you do this, you have a card that is user session specific, which is nice. And also now, our users will be able to switch between different devices. So we'll be able to switch between different devices, of course, when building the order. And they won't experience any service degradation if we dynamically scale in the meantime, which is also nice. So congratulations, that's what it takes to properly set up distributed caching. It's really not that much involved. Before I move on to the next subject, so getting closer to the more interesting stuff, I want to encourage you to read the official documentation to see what else is needed to have a good production deployment. There are a couple of things more to do. And also some of the generic methods that you saw, like get card, they're extension methods, you're supposed to write them, but they basically all they needed for is just for you to specify how to serialize and deserialize your objects. That's nothing weird. And in this documentation, you will find how to do all of this stuff. Okay, enough time talking about sessions. I wanted to start with sessions because they are a problem that everybody has to deal with, basically. And also because sessions and caching, even though we don't think about them that way, they actually are real coordination problems. But since as an industry we understand them fairly well, and when a problem is well understood, then you get an easy configuration option in your framework. But not every coordination problem is just as easy. So let's now start talking about the stuff that you don't find configuration options for in ASP.NET Core. So I mentioned in the beginning, I think we don't give enough love to intra-service communication problems, so coordination problems within the same service. And as a consequence, it's not trivial to map the whole space of problems that we can encounter and the relative patterns to solve them. So for this reason, I'll mention a couple more examples just to kind of give you a feeling to like a rough mapping of the space of problems that I encountered in my experience. So let's start with something from the opposite side of the spectrum, live chat applications. So raise your hand if you've used IRC in the past, please. Okay, oh, that's so nice. Quite a few hands, thank you. For those who have never had the pleasure of experiencing IRC, this is what the interface looks like. It's just text messages. The background is not always black, but kind of has to be. And it's all text messages. They're not persisted on the server. You're supposed to only see the messages that have been sent while you were online. Discussions are organized in channels, and after you connect to a server, you can then join an existing channel or create a new one, join more channels, more than one channel, and then after that, you'll be able to chat with the people that are in the same channels as you are. I'm going to use IRC as the main example, but the same exact concept is at the base of many modern collaborative tools and like multiplayer games. So for example, I'm building a multiplayer Sudoku game, and the architecture is the exact same as the one that I'll show for this example. The only difference is that here the messages are basically, once the front end receives the messages, they just get displayed in order, while in the Sudoku game, the messages change the state of the board for the user is seeing. So it's a relatively small difference. The architecture is precisely the same. So going back to the contents of our service box, let's say that now we pivoted, we are not doing e-commerce anymore. Now we are a live chat application. And let's say that we scale out, like in the picture. How do we make messages sent to one instance reach other instances? In the e-commerce example, there was no communication between users, right? So we could just simply distribute the requests across multiple instances, and that was it. But now, if a user is connected to instance 1 and another user is connected to instance 2, and they are in the same channel, how do we make them communicate? You might say now, why don't we just distribute channels among different instances and have clients make multiple connections if they want to join multiple channels? So if you want to join channels A and B, you connect to instance 1. If you want to join channels C and D, you connect to instance 2, etc. Well, guess what? If you try to do this, in my experience at least, you end up again with a lot of operational problems. Because now you must be able to address individual instances. And either your clients know how to do that, or your load balancer must understand how to route connections correctly. And it's the session situations all over again, basically. With the only difference that where before we needed sticky sessions, now we need a different routing scheme based on the channel name, for example. And also, dynamic scaling with this setup is annoying to make work. I wouldn't even know how to do that properly, honestly. And if you think back about the session situation, even though it was trivial, and everybody does sessions that way, and you don't even think about it, in that case, moving sessions to a distributed cache, by doing that, we were able to remove a lot of internal tension in the system. And in this other example, being able to connect to any channel from any instance has the same effect, because it's what allows you to treat your instances as cattle, not pets. You don't want to have to address your instances individually. So what we want is a way to keep a connection open between all instances, so that when one receives a new message, it can then broadcast it to all other instances. In other words, we want a PubSub system. Now, it might surprise you, but there aren't that many pure PubSub implementations out there. More often than not, what you will find are message queue implementations that also support PubSub as a message routing scheme. which is fine, but it has some performance implications that you don't want to deal with when you want like low latency at throughput scale, like in a real-time chat application, or especially stuff like mobile games. Sorry, multiplayer games, not mobile. Not necessarily mobile. So pure PubSub is a synchronous fire and forget communication pattern where producers publish messages on a channel and all the consumers subscribe to that same channel will receive them. Because it's fire and forget, there are no X, there are no acknowledgements. And because it's synchronous, there is no persistence. So both entities need to be alive and connected at the same time for communication to happen. So this means that if a client loses its connection, all messages broadcasted in the meantime will be lost for that client. All of this might seem quite limiting. So oftentimes you think, oh, I do want persistence. I don't want to lose messages if I lose the connection. But there are some situations, like the one that I'm showcasing, and especially the next one, where this is all you want. This is all you need. And every extra feature will introduce extra costs, extra complexity, delays, and for no benefit to you. So ZeroMQ and NanoMSG are two very, very cool socket libraries that allow you to implement PubSub and a few other messaging patterns. They're also brokerless libraries, so they're kind of low-level tools that you usually use to implement your own networking tools, basically. So they're also brokerless, so all the participants need to know how to connect to each other, while Redis PubSub is a brokered version of PubSub, and with Redis itself being the broker, so everybody connects to Redis, and Redis does the message routing to everybody else. And I can show you how to use it. It's like very, very simple. So, okay, I'm missing one of my desktops. Oh, okay. I see the PowerPoint has appropriated one of my desktops. Let me try to fix this for when we come back. Okay, just 1 second. So, PubSub, right? First of all, we need to start Redis. When you see like the cool graphics, you know that you loaded Redis. Then you want to connect to the Redis CLI to play with it from the command line. Redis is a key value store. If you've so raise your hand if you have used Redis in the past and you've used like Redis CLI, so you know kind of a little bit about it. Okay, that's cool. Quite a few hands, though. That's very nice. So this is Redis CLI, and you can use it to interact with Redis and like set keys, delete keys, do a bunch of operations. But right now we want to play around with PubSub. So I'm gonna launch 2 instances of it. One on the upper part of the screen, one in the lower part. In the upper part, I'm gonna subscribe to NDC, to the channel called NDC. Now in the other CLI, I'm gonna publish a message to NDC hello. And the moment I press enter, the message is published, the subscriber has received it. If there were multiple subscribers, they would all receive it, so it's a broadcasting mechanism. Another interesting thing that you can do is, instead of subscribing to a channel, you can do a pattern subscribe, so p-subscribe to, let's say, NDC star. So now I'm subscribing to every channel that starts with NDC. So now if I push a message to NDC, it will work. If I send it to NDC London, it will work. Same with, I don't know, oops, NDC Porto will work too. If I send a message to PyConf instead, the subscriber won't receive it because the channel name doesn't match the pattern. It's like very simple. And keep in mind that the interesting thing about this is that these channel names, they are just strings that get pattern matched by Redis. Subscribing to a channel, publishing to a channel doesn't allocate topics, use disk space, waste a bunch of memory. There is no heavy setup to create a bunch of new channels to subscribe to a channel in PubSub. The whole point of PubSub is to be extremely lightweight, more lightweight than it would be if it were something else, like a message queue system. Okay, great. So, I might surprise you. As I thought, let's see if I told you this already. Yes, I did. So in this case, the PubSub functionality for the chat application is precisely what we want, because again, going back to the live chat idea, you want to broadcast messages across all the instances, and PubSub is precisely what it does. And in some sense, PubSub is IRC, but not for humans, but for your applications. And there are a lot of applications that really would like to have this kind of tool to support what they're trying to do. Another thing is that I've talked with a few people, and people occasionally are confused by which tool does what. So if you would think that it would be if you think it would be a great idea to use Kafka or another more heavyweight system to power a live chat application, I recommend to take a look at least at this article that I wrote. It's a blog post that I wrote for our technical blog, and in it I talk about the difference between different systems like ZeroMQ, Rabbit, Kafka. I also recommend to check it out if you don't know which problem is solved best by each. And if you want to know more about the difference between like pure PubSub and stuff that is different things that call themselves PubSub, like Google PubSub, for example. And again, like event streams and ESBs are important communication mechanisms between different services, PubSub, I think it's equally important when coordinating instances of the same service, and it's really a shame that we don't spend much time talking about it, regardless whether you're using Redis PubSub or another implementation. So we covered two extremes of the space, and my next example is going to be closer to sessions. The concept itself is not new, like everything else in computer science, but I wanted to give a cool name to my take on solving it, and so I called it Memo Lock. So what's a Memo Lock and why should you care? There's a problem called cache stampede that happens when a service is under heavy load and there is a cache miss on a popular value. Raise your hand if you heard cache stampede in the past and you think you kind of know what it is. Okay, just a couple of hands. Okay, this is going to be very interesting then, I think, for some of you. So normally, on a cache miss, you generate an updated version of the missing value and then you put it back in the cache. You don't cache stuff forever. Cache tend to be ephemeral, so you're fine occasionally with losing what's in your cache. But also you time out, you want to expire the stuff in your cache over time because maybe the data that's cached is not, it becomes stale because it changed in the main database, so you want to recreate it after a while. And so these are two big sources of cache miss. Also sometimes the amount of data that you can cache is a small subset of your whole data that you have in your main database. So you can't cache everything. For these reasons, you will occasionally encounter cache misses. And the problem is that when generating the value is not immediate, and in the meantime, another instance is trying to do the same thing, you end up with duplicate work. So in this example, you can see that the server instance under Redis is trying to get foo from Redis, doesn't find it because that's the case of a cache miss that we were mentioning. So what it does, it goes onto the main database, tries to select foo or whatever the resource it is, gets back a query set, and then saves it into Redis. But oh no, in the meantime, there's another instance that's trying to do the same thing. And it just happens that they try to get foo before we were able to write back to Redis in the first instance. So what does the other instance do? The same thing, which results in a bunch of duplicate work. And under heavy load, this behavior makes bad things really go worse because you're bound to have more and more requests piling up for popular values. Imagine like if you're Twitter or one of those social platforms where whenever a big influencer does something, everybody rushes and storms because they want to see it. So, so what happens is that all these requests piling up, they cause more and more duplicate work. And if you're hitting the database, that makes generating the value even slower because you're overpowering the database. And that in turn creates a larger window in which the stampede could happen. So this is like a vicious cycle. The big things go really, really bad. And I read recently a tweet thread by Nick Craver where he was talking about basically the same concept, that whenever they had particular conditions were met in Stack Exchange, they would have some big keys that needed to be created and moved from the database to the cache, and that was a window large enough to cause a stampede. So how do we break out of stampedes? There are a few different ways to mitigate this problem. Some require really good statistical knowledge of your domain, so I'm going to skip them because they are too specific in a way, which leaves us with locks. You might not like them, but locks are the diet of choice for philosophers out of 5, and they're really not that bad if you use them with parsimony. So here's the idea in pseudocode. It's very basic, right? So you want to protect the value with a lock. So this way you ensure that only one process can hit the database at a time, which prevents basically the stampede completely. So I try to find foo on the cache. I don't find it. So before going blindly hitting the database, I first try to grab the lock, and I only go onto the database if I'm the one that wins the lock. Everybody else doesn't. On paper, okay, this sounds simple, but if you've done concurrency in the past, you know concurrency is never easy. There's always small problems that creep in everywhere. But let me show you how to do locks with Redis. So, okay, we're done with PubSub. Let's go back to Redis CLI. So I mentioned that Redis is a key value database, right? The keys are strings. The values can be strings or the data types. I'm gonna use strings in this case because they provide you an easy way of doing locking semantics. So if I set Loris to hello, I was able to set the key. I get Loris, and I get hello back, which is nice. I can also delete the key. Once I delete the key, I can't get it back anymore. Makes sense. But look what I can do with set Loris, hello, and x and x. And x stands for not existing, so it means that the command will only succeed if the key doesn't exist yet. So I run it, and it works because the key wasn't there. But let's say that I try to run it again with a different message. It's hi, and this time the command did not reply OK, the set, but replied nil, and there was no side effect because the key still has the old value. So with this command, if 2 instances run set and x at the same time, only one will succeed, the other one will fail. So that's what gives you an easy-to-use lock. Now, there's also another problem that this lock would not expire, and locks that don't expire are not that useful in the real world. So let's check how to combine an X with an expiring mechanism. So I'm going to delete this key, and I'm going to then recreate it with an X and EX with an expiring timer. So this key now exists for 5 seconds, but after 5 seconds, the key doesn't exist anymore. So this key expires automatically. And it's nice to have this in one place because then your worker, your service instance could crash, could lose connection, but that would not compromise the entire system. So again, this is another small piece that it's nice to have and makes really things easier when doing something even uneasy as concurrency. So going back to our simplified code, the pseudocode, the grab lock then becomes something along those lines, like set lock foo. It makes sense to have the value be a unique ID, because again, you want expiring on your locks because you actually want leases. You want a lease, not a lock. And having a unique ID helps doing something that's called fencing. It basically allows to service instances to understand who is owning the lock, because sometimes it's not obvious after a restart, and it's a small detail anyway. You can learn more about it once you get interested on the subject. But the basic idea works, and it doesn't require much effort. NX, EX10, and that's fine. Now, yeah, actually, let me go back a bit, because damn it, I'm skipping the interesting part. So, what do you do when you can't get the lock? And when you can't get the lock, you know that there is another instance that is trying to produce the value in the meantime, right? So what you want now is a way to get basically a real-time notification from the other instance when the work is done, when the value becomes available. And at that point, so what is it that you want? Like, you want a PubSub notification, basically. And what's interesting is that the live notification in this case is precisely what you want, because this is like the perfect example for PubSub, because the notification only makes sense while the subscriber is alive. If the subscriber instance dies and reboots, and you lost your stack state, all the application state, then the message loses any meaning. Like, the user will have gotten a 505 or whatever, 500 error code or whatever already, and they will have retried the request or done something else in the meantime. So these are the perfect example of messages that you don't want to persist. So for the sake of completeness, if we subscribe when we can't acquire the lock, it means that we need to publish on PubSub that we're done. In the opposite case, like when we can, or when we actually succeed at acquiring the lock. So a more complete version of this would be, you try to get the lock. If you do get the lock, then you get the value from the database or whatever, set it into Redis, so that the next time the get succeeds. But you also publish on PubSub that the value is ready. And at that point, the subscribers will be able to receive the notification. Now, if you've done concurrency, you know that there's a little bit more, but how much am I oversimplifying? Well, I'm not oversimplifying that much, actually. I'm only omitting two things in this pseudocode. The first one is timeout handling, because the lock expires, and that's nice, but you can't subscribe forever on PubSub for a notification that potentially could never come because the other instance has crashed and whatever happened. So what you want is basically to time out of the subscribe after a while. Or also maybe producing the value takes a long time. So after a while, you might want to send a message back to the user to say, check back again in a while, or stuff like that. And the second one, the second thing that I'm omitting is that you need to search for the key again after subscribing to PubSub. Because there's, let me show you the code. This should make it more clear. So this is a more complete code. We start by trying to get foo in Redis. We don't find it. If we do find it, we're done. We return it and we're done. If we don't find it, we try to acquire the lock. If we fail to acquire the lock, then we subscribe to PubSub. But between when we tried to grab the lock and we subscribed, the other instance might have completed the processing, have sent out a notification, and we lost it because we are not subscribed yet. And if you're doing this in Java, between this and this, who knows, there might be 3 minutes because of a garbage collection pause or whatever, right? So what you need to do is basically try to get foo again after you subscribe, because that way you close the window. There are definitely other ways of doing this. This is just one approach. But this is basically what my implementation does. This is, I'm going to showcase my library after this. And all of this is done by the library. The only thing you have to do is provide do work here. That's provided by you. Everything else is done by the library. And the interesting thing is that what you do inside your function is up to you. I used the idea of caching database query sets as the main example. But you could use the same approach and to shield serverless functions as a form of caching plus maybe quote-unquote rate limiting. You could use this library to shield, this approach to shield machine learning models, like deep learning models, AI. You could use it to shield like a endpoint that renders a PDF report. And you could, for example, render the PDF file, store it in a CDN, and save in Redis a URL to it. So you can get more clever with this. And it's really useful for a lot of things other than just straight up caching of database query sets. So this brings me to why I wanted to call this Memo Lock. So Memo Lock is memoization plus locking. And that's not a typo, it's memoization. It's not memorization, it's memoization. If you've never heard the term, you can Google it and read the description on Wikipedia, but long story short, memoization is the process of caching function calls. And so for example, let's say that you have a recursive Fibonacci, and you save in a dictionary the serialized version of the input that you give to the function, and as the key, and as the value, the output that the function gives. So you start caching function calls, and even recursive Fibonacci, which is a nasty function that really behaves horribly, even that will be good enough to use in practice, because every single time you try to recurse to a previous value, you'll just immediately hit the cache response, and you won't need to do the whole recursion every single time. So it's a legitimate common practice that you find also in other places. But since we are doing memoization in a distributed context, we also need locking, because otherwise we would not know when two instances are trying to do the same thing at the same time. So this is how I came up with the name. The library is on GitHub. My nickname on GitHub is Christoph-IT. The repository is called Redis Memo Lock. I have a C# implementation inside a demo ASP.NET Core project. And I also have a Go implementation. And the nice thing is that the two implementations can interoperate because they communicate through PubSub in Redis. So before I show you the code, I have a couple of things more to say. Let me see how I'm doing on time. Okay. So this is the 2019 Stack Overflow survey, and like last year, Redis has been voted the most loved database. I've seen that many of you raise their hands, so that really warmed my heart. Because occasionally I go to conferences and I ask people, do you know Redis? And a lot of people don't really know anything about Redis, and they just know that it's a cache. But how does a cache get on the top of the Stack Overflow survey? I mean, it's nice to make that a cache makes your service more performant and maybe saves your ass when there's a deadline. But I don't think that's enough to get a database on the top of this survey. So a lot of people say that Redis is fast, which is, yes, it's nice. But the reason why I think a lot of people love it, and I'm saying this in case you've never used Redis and you might want to look into it more, is because it's a tool that allows you to really solve easily these kind of coordination problems. And also because it's fast. But really, I think the more important part is like helping you really solve the occasional tricky problem that you encounter. And one point about Redis that you can find, for example, if you read the manifesto, inside the Redis repository on GitHub, there's also the Redis manifesto, which I think is an interesting read for a developer. And the point is that Redis is all about simplicity, which doesn't mean making things easy. It means making sure that you don't make things more complicated than they have to be. So, which is important, for example, in the case of doing non-easy things like concurrency. So, for example, you've seen that I had to write some code. I had to think about the problem. It wasn't like a immediate, complete vertical solution that solved it in one line. But at the same time, it's not super complicated. You can reason about it. It takes some effort, but then you have a complete understanding of what your system is doing, which is something that I really want to have in the things that I build. So the philosophy, one of the philosophies of Redis is to basically give you small orthogonal pieces, and then it's up to you to combine them. So like strings with the locking semantics plus PubSub, you combine them and you get memory. And this is how you get basically maintainability, speed, and all the stuff. Second thing, before the code, no, actually, I think this still counts as part of the first. I showed you this bar that should be like the spectrum of all the coordination problems. I showed you sessions, Memo Lock, and some kind of IRC-style chat to basically, as an example of applications that need to communicate in real time, like collaborative tools, some types of collaborative tools. What's in the blank space between Memo Lock and IRC-style chat? And the answer is I have no idea. So this is basically the result of, I don't know, just me thinking about the things that I encountered in my life. I've never found a book that methodically covers all this stuff. I'm sure there must be some piece of literature somewhere that covers something. And I also personally found a couple more examples that weren't, I think, interesting enough to put in the presentation. But there are a lot of things, I think, in there that we just see and maybe don't recognize. So one rule of thumb, one thing that I noticed is that, and I mentioned this already, but occasionally you find a service that is annoying to operate and you can't really put your finger on why. And like sticky sessions are something that now we're becoming more and more aware that if your service needs sticky sessions, there's something that you might want to improve in that. And so the idea is that if you find a service that is annoying to operate, maybe that's an indicator that the coordination wasn't handled properly when developing it. So something to think about. Okay, now, commercial break before the code. I work for Redis Labs. That's the company basically behind Redis. We are the home of Redis. We sponsor the open source development because Redis is an open source database, as I assume most of you should know. And we are also hiring, by the way. If you like Redis, let me know, or at least go on the website. The company sells Redis Enterprise, which is Redis plus stuff that enterprises like, that Redis doesn't provide out of the box. And you can get Redis Enterprise on premises, or you can have it in Kubernetes, or all the flavors of Kubernetes and manage it yourself, or, which might be a good idea, you could have experts run it for you, like us. And in that case, you can have it on AWS, Azure, GCP. It's everywhere. Or we can put it in your VPC. We manage it, and you don't have high latency. So the deployment is never a problem. Okay, now onto the code and the demo. So to show you the code, I need to move this here. Okay, let me see if it's, is this big enough? I think yes. Okay, so I'm going to show you the interface. Again, it's not really involved. So first of all, I instantiate, here there's my new instance of Redis Memo Lock, which is a simple class. It's in another file. It's like a couple hundred lines of code, I think, not that much. The only thing you have to pass to it in this case is an instance of the Stack Exchange Redis client, and a string that represents a namespace for the objects that you want to cache, so to group them together and make it easier to inspect what's going on with your Redis instance. So there's a sample handler. And in this case, what's happening is, the idea is, I want to get the resource named ID, which I'm getting from as a parameter from the URL. If it's in Redis, then great. I get the result immediately back from the library, and I'm done. But in case the value is not there, you also have to provide a Lambda function that whose job is basically to generate that value and then return it so that the library can store it in Redis and return it to the caller. And so in this case, I'm not doing anything useful. I'm just printing a log line, which says, yeah, I'm working hard. Then it's going to sleep for 3 seconds, and only then it's going to return the value, which is, again, just a dumb string. But that's just because it's a demo. So let me show you this stuff working. .NET run. So while .NET loads, I prepared here, I think it was simple / query / foo. Yeah, I had it there. Okay, so these represent two clients. I'm going to run the I'm going to hit the same endpoint more or less at the same time. And what you're going to see is that only one of the two calls triggers the log line in the bottom window, because only one of the two calls is going to do the actual work of producing the value. The other one is going to wait on PubSub for the result to come. And you also see that the result comes at the same time for both, basically. Oops. Damn it. This. Let me try again. Why am I getting this? OK, that's great. Weird issues.
You transposed query in simple.
Did I? Oh my God. Yeah, thank you. Bad memory. Thank you, guy.
And you spelled query wrong.
Simple. Foo. OK. You know what? I'm also going to flush the database so that I can properly demo this. OK, so the database has been emptied, so it's like a clean state. Let me try this again. Oh. OK, and it works. So the first log line at the bottom is for the previous call. The second line is from this current call. And both got the same query, the query set result at the same time, but only one of the two triggered the work, which is nice. This is the simple interface. So I also added a bit more of intelligence to this thing. So I added this another example endpoint where the idea is that I'm building a report, a PDF report or something, but I don't know how long it will take. So it would be nice to be able to extend the lock in case I discover that I need more time. So this is the same interface, except that if instead you call this overloaded method where the async function takes a parameter, the parameter that the library will provide to your function is a sync function that basically renews the lock. So it allows you to extend the lock for more time. And it's nice because then you can use it. And if you call this, it's going to work like the previous example. But in this case, it will allow you to, again, extend the lock. And it will throw out an error if the lock expired in the meantime. So it will ensure that your lock renewal kind of makes sense. It's not like you're going to, out of nowhere, steal a lock and like produce chaos. In this example down here, I'm going to do the same. But in this case, I'm going to basically delay to match the call to renew, and in this example, if you run it, you will basically see that it returns a timeout exception, and very trivial. Another thing that I did, which is, I think, interesting, and I'm going to demo this, is, yes, that's this one. So here the AspNet Core application is launching a Python program. And the Python program is not gonna, it's gonna be launched as a separate process, and it's not even gonna communicate anything back to the .NET application, because they will communicate through PubSub. So let me show you the code in the Python application. So again, it's a very simple example, but the idea is that I'm using the NLTK library. It's like a natural language toolkit to do stemming of a word, just again, as an example. And once I'm done, this application knows how to basically use the same naming scheme for resources and PubSub names, and it's gonna basically notify the result through PubSub. So in this way, you don't even have to do all the annoying inter-processing communication through std out or whatever. Let me see if we can make this work. So it's called x/stemmer. Let me think of a word that we can stem, like. I like this word. I like this word because it's one word that has my name, my whole name in it. There aren't that many, especially in Italian. I think in Italian, so folkloristic in Italian is folkloristico, and that's, I think, the only Italian language that has my name in it. It's a small detail. Folklorist, OK. So as you can see, we launched the Python program through the C# program, and it worked. No annoying std out stuff. And what now is a process could very well be a Lambda function somewhere, a serverless function. So yeah, it makes the interoperability nice because the integration surface is relatively small and Redis is ubiquitous. and that's automatically propagated, broadcasted through your whole instances in case you're, again, scaling out and using a distributed system. So that's the main part of the demo. I have one last example because I want to stress out how nice the integration surface is. And Guy, if you don't mind helping me out, I have a dumb joke and dumb routine that I'd like to show you. I think we still have, we do have enough time.
Can everyone hear me okay?
Yeah, I think if you stand here, I think the microphones will be enabled. So you know how some AI startups, they want to launch a product, but they don't have already figured out the AI part yet. So what they do occasionally is that they have Mechanical Turk setup going on, right? So they sell to you the AI thing, but the AI is actually, it's I, but not really A. So it's intelligent, but not much artificial, right? Very genuine artificial. Oh, I think some would say it's not just AI, it's also like genetic programming, right?
So am I your mechanical American?
Yeah. So let me launch the joke. Flash joke. Okay, right?
Greetings, humans. It is I, the great .NET Core runtime. A task is bestowed upon you. Determine the following. How much wood would a woodchuck chuck if a woodchuck could chuck wood? Provide the correct answer in freedom units. You may now proceed.
Okay. What are freedom units?
I'd say 3 quarts.
Three quarts. Quarts?
Yeah.
Okay. So again, you saw how this thing works. So the integration surface is so small that I can just like type publish to ext. There's the naming scheme that you need to know, but I set that up. The naming scheme could be simpler. You can do it whatever you want with it. In this case, I do ext/notif : joke, I think. And this is where I would produce the value. But maybe I want to leave the .NET Core hanging, and I want to trigger the timeout. Because, again, there was a recent blog post by Armin Rocher. I hope I pronounced the surname correctly, probably not. But about how it's important to do back pressure correctly in these kind of libraries. And yeah, the timeout triggered, and all segmentation faults for our .NET Core engine. But let me trigger the computation again. This time, we're going to provide the value correctly. You said 3 quarts?
3 quarts, yeah. I don't actually know how much a quart is. I just know that fire was measured in it.
Okay. I need quotes, because there's a space.
You retorted 3 quarts as results. I trust your answer is correct, for I am the mighty .NET Core runtime, and I do not intend to check.
Yeah. And that's it. Thank you very much.
Thanks.
Okay, if anybody has a question that they want to ask while I'm here, raise your hand. Otherwise, I'm going to stick around, and you can ask afterwards once I sit down. Oh, down there, you'll have to speak very loudly.
Come forward.
Yeah, thank you. I repeat it for the microphone in any case.
Trivial, but it sprang to mind immediately when you showed a Redis set that didn't set if the value already existed.
Yes.
I've never used Redis. Does it also have try delete? So if the value exists, delete it and return it. If the value doesn't exist, error?
Yep. I can show you. So in general, sorry, let me repeat the question. The question was that set can also has the NX option that makes the command fail if the key is already existing. And the question was, is there like a version of delete that tells you when you're trying to delete something that is not there and reports an error? So the answer is that yes, this kind of reporting, I think, is everywhere in Redis. You always can inspect the result of a command that you send. The slight philosophy difference is that these things usually are not reported as errors. So they're reported as statuses. Let me show you. So here I'm in Redis CLI. and I set Loris to hello, and then I delete Loris. If I delete Loris again, you can see that the first time I got a 1, the second time I got a 0. 1 and 0 are like true and false. This is gonna, by the way, be improved in Redis 6, so you're gonna get like a proper true and a proper false, because there is a new version of the protocol. But regardless of these small details, the general philosophy of Redis is not to report errors, but to report the state, the outcome of a command. So for example, if you try, there are also lists and other sets and other data types, and if you try to add something to a set that doesn't exist, Redis will implicitly assume that you want to start from an empty set and then add the value in. If you try to increase a number, for example, we deleted Loris, right? Let's say that now I want to increase the number stored in Loris. The key doesn't exist, but the assumption is that since it doesn't exist, we can assume it should default to 0, and then we move from there. So yeah, that's the Redis philosophy. Okay, any other question for the podium? I think not, so we're done here. Thank you very much again.